Now we'll talk about a model that basically becomes useful to predict the magnetic moments of alloys of first row transition metals. It's the so-called rigid band model. And it's based on the idea that the structures of 4s and 3d bands do not change significantly across first transition series. So when we look at the differences in the electronic structures, it's mainly due to the changes in the Fermi level. Okay, so the model is the following. The structures of 4s and 3d bands do not change significantly across first row transition series. So the differences in the electronic structure are due to changes in the Fermi level. Okay, so if the Fermi level lies in the 3D band, we have more electrons in the lower energy spin direction, leading to a spontaneous magnetic moment, because the exchange splitting is dominant for 3D band. So you can see here 3D band and 4S band schematic illustrations. You can see that the dash line, that's the 4S band, is not exchange split, but there is a significant exchange splitting in the 3D band. So here you can see it. There is a shift. So that's of the amount that is mu 0 mu b times H exchange basically. So we have significant splitting in the 3D band. So that's my first remark. The exchange interaction is dominant for d electrons. So that means I have exchange split bands here. So you can see that one spin subband is moving up with respect to the other. And if the Fermi level lies within the 3D band, we have more electrons in the lower energy spin direction. So that means this is going to lead to a spontaneous magnetization. Okay, so this explains why we have ferromagnetism in these materials, really. Now, another remark is that if you remember, we had a similar situation in polyparamagnetism. So this is remark 1, this is remark 2. Now what was happening in paramagnetism? The free electron bands in the polyparamagnetism are also split, so it looks exactly like this. However, the reason for the splitting is different. They are split in polyparamagnetism. The idea is to minimize the Zeeman energy, so it's due to Zeeman energy, and which was minus mu 0 m dot product with the applied magnetic field. Here it's the exchange field we're talking about. Okay, so let's take a closer look at these elements, zinc, copper, and nickel, and you can see that the Fermi level is coming down. So this is E Fermi of zinc, this is E Fermi of copper, this is E Fermi of nickel. So the Fermi level is coming down, so we have d electrons or empty states in the d band. So for zinc, if you look at this carefully, the Fermi level is above the 3d and 4s bands. So we have 3d and 4s bands completely full. Therefore, we expect that there is no magnetic moment per atom, so no moment. For copper, on the other hand, if you look at copper, the copper Fermi level lies within the 4s band, but above the 3d band. So 3d is completely full, but 4s is not full. But we don't have exchange splitting in 4s, therefore we don't expect any magnetic moment. So for copper, 3d is full, 4s not full, but no exchange splitting in the 4s band. So therefore we find that copper has no spontaneous magnetization. Now let's move on to nickel. Now when we move down a little bit further, we see that it has both 4s and 3d electrons. That basically adds up to a total of 10 valence electrons. So if we look at how many electrons are in the 4s band, we find that we have on average 0.54 electrons in the 4s band. So that means there is no contribution to the magnetic moment, and we have the rest 9.46 electrons in the exchange split 3d band. Okay, so if you calculate the number of up spins plus number of down spins in the 3d band, it is 9.46 in the 3d band, 9.46, and we have, if you look at this carefully, for up spins the Fermi level is above the 3d subband. So, but for down spins it is not. So this was for up and this is for down, and you can see that because of this I have the total number of up spins is 5, but the total number of down spins is 4.46. Okay, so then you can see the net number of spins that are not balanced. So 5 minus 4.46, we have 0.54 unbalanced electron spins, not balanced, not compensated for. Therefore, we find that the magnetic moment is 0.54 Bohr magnetons per atom. Okay, now on the other hand, if we, for example, look at iron, if we keep going down, so the next one is basically iron. This is how it goes: nickel, cobalt, iron, manganese, etc. So we're going down in the band. Now iron has 8 valence electrons, and it has 0.95 electrons in the 4s band, which is not exchange split, so there is no contribution to the magnetic moment per atom. And we have 7.05 electrons in the 3d band. So number of up spins plus number of down spins is 7.05 in the 3d band, and the number of up spins is 4.62, the number of down spins is 2.42, and the net moment mu is 2.2 Bohr magnetons per atom. So that's basically the difference between number of up and number of down spins. That is 2.2, the imbalance between the numbers. If you go further down, so let's put a remark here, the situation gets a little bit more complicated. In manganese and chromium, the exchange interaction is too weak, and the band energies are larger, so there is the rigid band model seems to be not working so well. So they show a more complicated situation and antiferromagnetic coupling between the spins. Okay, now there is a useful result that comes out of this. For the number of d electrons and the number of d electrons greater than 7.5, the magnetic moment per atom can be written as 10 minus nd Bohr magnetons. So the slope here is minus 1, and you can see that when you make alloys of chromium, manganese, iron, cobalt, nickel, copper, etc., we find that there is this linear relationship for nd greater than 7.5, the minus 1, and it's actually more or less linear up until this point also. And we find that the maximum moment is obtained is for an iron cobalt alloy with roughly 2.5 Bohr magnetons per atom magnetic moment. And the saturation magnetic moment is more or less linearly dependent on the number of d electrons. So that's what you can see from this curve, which is called the Slater-Pauling curve. So this basically tells us how the magnetic moment will change when we make alloys of different elements. So here I have talked about making an alloy of iron and cobalt, and you can see that there is a particular combination here which gives me roughly 2.5 Bohr magnetons per atom. That's the maximum point. Okay, so let's take a look at our localized moment theory and band theory, and let's compare the two. So in the localized moment theory, we have valence electrons that are all in bonding states. The model can explain the temperature dependence of the susceptibility, which is C over T minus theta. It also explains how the saturation magnetization differs from capital N times M as a function of temperature. It works well for lanthanides. Lanthanides have 4f electrons, so 4f electrons are localized, so it works well for lanthanides. Now in the band theory, all valence electrons ionized that are in anti-bonding states this can explain non-integer magnetic moment per atom. It works well for first row transition metals and, for example, for things like nickel 3 aluminum alloys and metallic ferromagnets. Now in reality, so there's let's put a remark here. None of these pictures are complete. In general, transition metals show both localized and itinerant electron characteristics. So in general, it's a combination of these two. Now, our understanding of the ferromagnetism and calculation of magnetic moment per atom is, as you can see, too complicated. There are two different views. We can assume that all moments are localized, or we can assume that all moments are due to free electrons. But a more sophisticated theory can account for the magnetic moment per atom. So the future developments in theory is based on DFT, the density functional theory calculations, to predict the magnetic moment per atom for an element. So it is not straightforward to predict from first principles what the magnetic moment per atom will be for each given element, because the situation is complicated by the fact that we have contributions from localized moments and itinerant electrons as well. So let's summarize. In the rigid band model, we're saying that 4s and 3d bands, band structures are not changing significantly as we go through the first row transition metals. What does change is the level of the Fermi energy, and if the Fermi energy lies within the 3D band, because the 3D band is exchange split, we will have an imbalance between up and down spins, leading to a net magnetic moment per atom. In comparison to polyparamagnetism, there we had the splitting of the bands due to the Zeeman energy rather than exchange field. So we looked at zinc and copper, where we had zinc 3D and 4s completely full. Copper 3D is full, but 4s is not full. Since 4s is not exchange split, we have both of them giving no moments. Nickel, on the other hand, has the Fermi level at the top, right at the top of the spin up subband, but it is intersecting the spin down subband. So it has some empty states there. So that gives us 0.54 electrons that have a spin up that is imbalanced by spin down electrons. And similar situation for iron, we have 0.95 electrons in 4s, 705 in 3D, and there is an imbalance of 2.2 up spins, therefore 2.2 magnetic moments μb per atom. This situation, this simple explanation does not work so well for manganese and chromium, where the rigid band model fails. So there is significant changes in the energy bands, and the weak interaction, the exchange interaction is too weak and more complicated, and sometimes even antiferromagnetic alignment is preferred. There is a useful Slater Pauling curve for the number of d electrons greater than 7.5. There's a more or less linear relationship between the magnetic moment per atom and the number of the composition of the elements. So you can see that for a cobalt iron alloy we have a maximum. So it's about 2.5 Bohr magnetons per atom. So this curve can be used as a reference to design alloys of different materials to decide what the or more or less what the magnetic moment per atom will be in the alloy. And finally, these two pictures, localized moment and band theory pictures, can be compared. In the localized moment, valence electrons are in bonding states. Band theory, they're in anti-bonding states. They're free electrons. The localized moment theory can explain the susceptibility, temperature dependence, C over T minus theta, ms over m0 as a function of temperature. The band theory can explain non-integer magnetic moments per atom. The localized moment theory, as an example, works very well for lanthanides, where the 4f electrons are localized. Band theory works well for example, for nickel-3 aluminum. But the transition metals usually show a behavior that's in between localized and itinerant electron characteristics. So in order to guess from first principles what the magnetic moment per atom in an alloy will be, one can refer to more complicated theories like density functional theory.